So here we're going to learn a little bit about magnets and magnetism and how it relates to electricity in this topic. So if you have a magnetic material, right, it is made up of a whole bunch of atoms, and these atoms have electrons, and the electrons are all spinning. And there's areas of a magnet that we call domains. So these are all considered sort of domains. And within a domain, all of the electrons are spinning in the same direction. So when you learn in chemistry about electron spin, I know not everyone in here is taking chemistry, but we learn to draw electron spin by representing it with an arrow. So in the case of a magnetic material, all the electron spin is aligned within these domains, and all of the domains are pointing in the same directions. This is considered something that has a magnetic quality. Whereas if we had some other material that was not magnetic and there's these domains, these electrons would be spinning in all different sorts of directions, and this would be considered non-magnetic. All right? So if we were to have a bar magnet, let me just go ahead, grab another sheet. Bar magnets have poles based on the fact that all of their electrons are spinning sort of in this direction. So let's say we have a north end and a south end. Magnetism is a field force, just like electricity and gravity. So there is a field around a magnet called a magnetic field, where a magnetic force would act on another object coming close to it, or another magnetic object coming close to it. And there's a convention for drawing field lines, right? So field lines for electrical charges always point away from the positive and towards the negative. Well, for magnets, field lines always point from the north to the south. So if we were going to draw the lines around this bar magnet, it would look like this. We'd have some coming in this way. We'd have some leaving this way, right? So that demonstrates the magnetic field lines around a bar magnet. Now, if we look, let's say we were to cut this magnet in half, right? That means we would have still two smaller magnets, but they still would have a north and south pole. So the magnets are always going to come in dipoles, in pairs. Whereas electric fields, we know that we could have a positive charge or a negative charge, but magnets are always going to come with this sort of pair arrangement of north pole and south pole. Now, when we bring two magnets close together, there is a magnetic force that is exerted based on the magnets coming into each other's fields. And just like electricity, we have that opposites attract, right? So in this case, we would have an attraction here between the south and the north end. And like magnetic poles repel, right? So if I were to have an example where I had two, north poles pointing at one another, then I know that there would be some repulsion in this direction. Hopefully this is all sort of basic and review for you. So what's important to pull out of this is that there are electrons that spin within a magnetic material that generate the magnetism. So there is some correlation between electron or electrical movement, we'll say charge movement, and magnetic fields, which I will talk more in the next unit, right? That these regions where these electrons align are called domains, and if all the electron spin domains are aligned, we have a magnetic material. If not, we have a non-magnetic material. Electric field lines point from the north to the south of a bar magnet, and bar magnets always come in poles. Because there's a field, there will be a force exerted on a magnet or an object that comes within that field, and like magnetic poles are going to repel and opposite magnetic poles are going to attract. In the next video, I'll talk a little bit more about how the movement of electrical charge can cause a magnetic field and vice versa.